In this video, we are going to be looking at Gay-Lussac's law. We are going to look at some experimental results using a simulation, as well as some conceptual understanding of why it works from the context of the kinetic molecular theory. So first of all, let me review that Gay-Lussac's law is like this. It states that when you increase the temperature, the pressure of the gas will also increase, and when you decrease the temperature, the pressure of the gas will also decrease. But since we are looking at temperature and pressure, we have to keep the other variables constant. So in Gay-Lussac's law, number of particles and the volume is kept constant. So basically here, you have a direct proportionality again. When this increases, this increases. When this decreases, this also decreases. So in order for us to kind of show this experimentally, let us look at an animation. Okay, so this is an animation of a confined gas. And take note that we are keeping the volume constant. So if we are keeping the volume constant, then I have to kind of go here and check this value here. So I am holding the volume constant. That means the walls of this container will be rigid, meaning the walls cannot expand, the volume inside cannot expand or cannot shrink. The volume stays the same. Okay? And again, as for the second assumption is you keep the number of moles, number of particles inside constant. That's no problem because in our animation, the number of particles inside, this is a sealed container. So in other words, the particles cannot come out. You cannot add more particles. So the number of particles here is constant. So let's do the experiment. So first of all, let's look at the value here. The temperature is 300 Kelvin. And the pressure, which is this one, is around 27 atm. So fluctuating around 27 or 28 atm. So let's kind of jot that down. So the pressure is around 27 atm. And the temperature is around 300 Kelvin. Okay? So let's take a look at this. If this is true, if we increase the temperature, will the pressure increase? Okay? So now I am increasing the temperature here by adding energy to the particles. Now look at the temperature. Now the temperature reaches, let it reach 600. There. 600 Kelvin. And if you notice, the particles are moving kind of faster. If I cool this down to around 300 Kelvin, notice that the particles are moving, or I can even probably move it, decrease it even lower so that the change is kind of obvious to you. Let's do 100 Kelvin. If you notice here at 100 Kelvin, the particles are moving slowly. Okay, but more importantly, we are looking at the relationship between temperature and pressure. So let's look into that. So here the pressure is now 10 atm. Okay, it's 10 atm and the temperature is around 100 Kelvin. So let's just have that. So if the pressure is 10 atm, the temperature is around 100 Kelvin. Okay, so again, the pressure is 9 atm, 10 atm. The temperature is 100 Kelvin. And if we increase the temperature to the original, which is around 300 Kelvin, let's get that to 300. Notice now the particles are moving faster. 300, that's 178, 300 there. Around 300 Kelvin, notice the pressure now is around 28 atm. So it looks like this. Around 28 atm, the temperature is 300 Kelvin. But around 9 atm, the temperature is around 100 Kelvin, right? So this is a proof that that if you really increase the pressures from 27 or decrease the pressure from 27 to 10, decrease the not pressure, decrease the if you decrease the temperature, from 300 to 100, decrease the temperature, the pressure also drops. If you increase the temperature from 100 to 300, the pressure also increases. And if you notice, the proportionality here is kind of equal. So you have here 300 to 100, that's around 1/3. And 28.7, which round it off to 30, to 9 or 10 is around 1/3 also. So when you increase it by when you increase the temperature by 3 times, the pressure kind of increases to 3 times. When you decrease the pressure by 3 times, the pressure also decreases by 3 times. So that's kind of the experimental data. So again, let me do this one more time. If we look at this 300 Kelvin and the pressure, if we increase the temperature, now the temperature is around 400. Look at the pressure go up also. And if you decrease the temperature from 600 going down to around 400, the pressure also drops down. So that is essentially what the Gay-Lussac's law is about. Now, how can we think about this conceptually, not by looking at experiment, but just simply using what we know about the kinetic molecular theory? Well, it's actually pretty simple, because remember that temperature, as we have discussed a while back, is simply just the average kinetic energy of all the particles in the gas. So therefore, it stands to note that if we increase the temperature, essentially what you're doing is you are making the particles inside the container move faster. Okay? And if they are moving faster, that means they are hitting the wall more violently. So if they are hitting the wall more violently, again, there is more force. And the area is the same, because remember, we keep the volume constant. So the area is the same, the surface area inside. So if the force becomes bigger, the pressure becomes bigger, piles up. So when you increase the temperature, the pressure also increases. Okay? Now, if you decrease the temperature, again, decreasing the temperature means you are lowering the kinetic energy of all the particles. So the particles kind of slow down in their movements. If they slow down, they hit the wall still, but not as violent, or not not with a forceful, not with the same force as when they were more energetic. So as a result, this force here becomes smaller. You still use the same area. So as a result, you produce a small pressure. So when you drop the temperature, the pressure also goes down. So you see, just by thinking conceptually about, okay, what happens when you increase the temperature? What happens to the molecules, the moving molecules, according to the kinetic theory of kinetic molecular theory of gases? If you just know what temperature is, what pressure is, you can kind of piece them together conceptually, even without looking at experiments. Okay, so that is it for the Gay-Lussac's law, and how we kind of conceptualize it using experiments that we can see in simulations, and also in terms of conceptual understanding, just based on what we understand about how the molecules in the gases are moving, and how they kind of define what temperature and pressure is.